So we're going to move to the second part of the event, which will be like four presentations on four emerging pathways for CDR, and we're going to start with Phil Renforth, who's associate professor at Heriot-Watt University, specifically within the Research Center on Carbon Solutions. Phil is one of the world's leading experts on CO2 mineralization and has been doing a lot of great work on that emerging but extremely important pathway. Phil, the floor is yours. You have 15 minutes for approximately, and we'll take, for everyone, we'll also take Q&As for Phil's presentation. So please do continue to send your questions on the Q&A box at the bottom right, and we'll take some of the questions at the end. Phil?
And I might add, Phil is one of our favorite grantees.
I'm sure really you say that to all of the grantees, but thank you for that. And thanks, Ben, for the invitation. I'll try and share my screen. Hopefully you can see that.
Yes, we can see it. It's perfect.
Lovely. Okay, and I'll start my timer as well. So, but yeah, if you can give me a 2-minute warning, Ben, that would be appreciated. Okay, so great, thanks. I'm going to spend the next maybe 10 to 15 minutes just chatting through the potential of carbon mineralization. So I suppose, you know, the history of carbon mineralization has been quite interesting. I mean, people have been thinking about locking CO2 up in minerals pretty much for as long as we've been worrying about climate change. So in some ways, the ideas sort of stem from the late 1970s when folks were looking at how the natural carbon cycle might work, particularly through geological time. And that sort of then precipitated a bunch of ideas around using minerals to capture CO2. I'm going to try and sort of give you my take on it as it stands at the moment, particularly for atmospheric CO2 capture. So if you haven't come across the idea before, the idea is you take artificial materials or potential natural minerals, and you want to form essentially a new mineral, either a solid carbonate or a dissolved bicarbonate. And I'm probably not going to touch too much upon the dissolved bicarbonate side, because I think Brad Hack might talk about that in his presentation around ocean-based approaches. But you know, probably the key thing is the arrow in the middle. You know, how do you go from turning those natural or artificial materials into solid carbonate? And the idea here is that, you know, the CO2 is now locked up in a new mineral, either as a solid carbonate mineral or as a dissolved bicarbonate in the oceans. There's a bunch of ways to do that, and this is a conceptual cartoon of different ways that have been proposed, from taking CO2 directly from the air with direct air capture, and then putting it underground into a suitable rock formation. This is sort of what Climeworks and Carbfix are doing in Iceland at the moment. There's ideas around extracting minerals, so rather than leaving them underground, extracting them and putting them into environments in which they will dissolve and react with CO2. And this is maybe where the sort of crossover with Brad's talk is that some of the ideas are around adding minerals either directly to the ocean, or putting them in environments where the ultimate destination is the ocean. So there's a sort of range of ideas out there. This is a book chapter that we've currently got in preparation, so hopefully that will be out sometime in the next few months. So watch this space. But it's a general overview of the geochemical negative emission technologies. And well, why are people thinking about mineralization, CO2 mineralization, particularly with atmospheric CO2? Well, there's been a bunch of suggested positives or benefits, and that the scalability is potentially quite large. Decadal scalability, sort of on the order of hundreds of millions of tons of CO2 per year, are quite reasonable. But sort of on sort of long-term scalability, it's reasonable to say that it will be greater than a gigaton of CO2. And I'll sort of justify why I'm saying that in a second. But there is also sort of potential for much larger than that, maybe even greater than 10 gigatons of CO2 per year. So when we're talking about removing, of the need to remove 10 to 20 gigatons of CO2 per year, a scalable potential, on gigatons really quite significant. The other is around cost, and I think folks have talked about. I've seen suggestions of niche opportunities for mineralization, and that's specifically if you're producing sort of byproducts or products from the process. Those may have scalable potential issues when you end up saturating markets, but I've seen suggested costs sort of below $50 per ton. That really is exploiting sort of niche opportunities. But sort of scalable potential in terms of costs could be, is still really quite interesting. Pretty much virtually stating that it would be able to be done for under $500 per ton of CO2. That's sort of, you could probably bet your mortgage on that. It's probably reasonable to suggest that there are processes out there that can operate for under $100 per ton. I mean, I've seen folks suggesting that you can do scalable potential for close to $50 per ton of CO2, but I'm a little bit skeptical. But I think those things sort of in and of themselves make this quite interesting. And the end product of the reaction is a material that is more stable, a sort of a form of CO2 that is more stable than CO2, so it won't re-release back into CO2. Particularly around mineralization, there are some questions around the ocean alkalinity side, but I think it's pretty reasonable to say that it's a long-term carbon storage. So taking those three things together makes me think that so taking those three things together is sort of generated quite a lot of enthusiasm within this space. And I suppose, just in terms of scalability, there's a couple of quick slides. I mean, if you just trying to visualize it, if you take the shapes on the screen as 1 gigaton of CO2, the bottom left-hand corner, and then all of the carbon in the atmosphere, if you could squeeze that into a box, this is sort of the relative scale. And then if you look at, the carbon in the Earth system, so the stuff that's in contact with the atmosphere, you have all of the plants and animals, the above ground biomass, everything that's in the soil, and then the oceans, and the little color sliver on the end of that is the surface ocean, which is sort of in contact on a yearly basis with the other boxes, and then the deep ocean, which is sort of in contact with the Earth system on a sort of 100-year time scale. If I was to then put in what the potential of capturing CO2 is for rocks at the Earth's surface, it would look something like this. So you've got like an enormous bog cube of potential and that's just the silicate rock potential. So there's an enormous amount of rocks at the Earth's surface. I mean, I find this actually in some ways a little bit disconcerting, is that all of the CO2 is thermodynamically likely to react with that, but it doesn't because of kinetic limitations, and that's why the processes to facilitate that reaction are really quite important. In terms of scalability, this is a little bit of work we've done quite recently, looking at a potential in the UK for scaling extraction. And this is rock extraction in the UK over time from 1900 through to present day, and what maybe future aggregate demand, crushed rock demand is. So if you look in the sort of 1960s, the maximum increase we had was sort of on a 10-year rolling average was about 10%. So, if we constrain future production expansion by that, we've sort of come up with three potential scenarios. So one around no increase in number of mines, one around the sort of increasing to the sort of previous maximum, and then another one looking at sort of the same sort of magnitude of increase from post 1950 through to 1990. So we were trying to constrain it by sort of reasonable scenarios, and ultimately these are the numbers that we came up with. Sort of something on the order of in the most extreme scenario, the largest increase, we're talking maybe something on the order of 160 million tons of rock per year by 2050. That's sort of on the order of 64 million tons of CO2 capture potential from that material. So, you know, that might not sound a lot in terms of global requirements, but, you know, in terms of the UK, that's really quite significant. I mean, the UK expects to remove something on the order of 100 million tons of CO2 per year from the atmosphere by 2050. So, you know, we have the potential in the UK to at least sort of have a significant impact on our own policy demands. So, you know, in some ways it's quite interesting to think that, you know, maybe it isn't the extraction that is going to limit these processes, which is one of the criticisms that's been usually leveled in the past with mineralization. So, and, you know, the UK is a relatively small country as well. You know, it's got, you know, relatively unremarkable geology. Actually, I shouldn't say that. I mean, you can hear my membership of the Geological Society being ripped up. I should backtrack. We've got remarkable geology, but not a huge amount of it. You know, the Deccan Traps in India, which is an enormous basalt province, is about the size, twice the size of the whole of the UK. So it's, you know, there's resources out there in the world that, you know, could be exploited for this. And in terms of waste materials or byproducts, you know, that has potential, you know, at least by the end of the century, to do multi-gigaton CO2. And I should say, you know, we a team led by Southampton University and Liam Bullock sort of revised the mine waste component up from my previous estimates. So it's, you know, there's potentially quite a large amount of natural materials that could be extracted, and artificial materials that could also contribute. Okay, and then maybe just so, you know, what probably isn't going to limit this is the resource. It's sort of how we exploit that resource for CO2 removal. So I've just got a very quick diagram here, which might be able to sort of chart some of the processes out there. I mean, if you sort of give me a bit of rope and say, well, you know, if we put on one axis sort of passive and intensive processes, this isn't equal to cost, by the way. So, you know, it's passive processes are, you know, low pressure over a long period of time. Intensive processes are sort of higher pressures over a shorter period of time, not equating to cost. And we put feedstock onto the y-axis. So we've got natural materials that we could react, byproducts or wastes, or materials that we specifically create for the purpose of reacting with atmospheric CO2. Well, you know, there's a bunch of ideas and projects that have sort of been started in university groups, and, you know, maybe up in this corner we might have, you know, what we might call enhanced weathering, you know, and there's a sort of ideas around using byproducts in passive approaches. Carbon Vault is the, you know, interesting project by De Beers looking at mine wastes. You know, but there's projects up in this corner which are more sort of intensive processes using direct air capture, but also reacting them with minerals. You know, that's sort of what you might call classic mineral carbonation. And then there's also maybe just sort of an honorable mention to, you know, electrochemical processes like planetary hydrogen and CMATE that sort of accelerating weathering, but sort of an indirect electrochemical approach. And then there's a sort of ideas around creating minerals specifically for reacting with atmospheric CO2. And these are sort of the more metal oxide looping approaches. And I think the point I'm really trying to make is that there's a lot of blank space on this diagram. And I think, you know, even, you know, this is obviously a space that's been thought about for quite a long time, but, you know, there's still a lot of unknowns within this. You know, we're trying to sort of fill in some of that around our iron and steel slag project, but, you know, we're only one project in that sense. And, you know, there's plenty of sort of unknowns of where, you know, creative minerals might actually sit within that. And I suppose the other sort of point is that there's more than just two axes to this. You know, there's, you know, obviously the ocean alkalinity enhancement, which hopefully we'll talk about later, but that adds, you know, another dimension. There's locations where these projects might happen, supply chain and technology readiness level implications, you know, emission intensity of the energy and the raw materials, the secondary benefits, the potential environmental impacts, the social issues and implications, you know, the capital intensity of the way the projects are financed, And then maybe probably even bottom to that list, maybe not really that important at the moment, is ultimately the nth of a kind cost. I'm just getting
2 minutes, Phil.
Oh, great, yeah. And maybe just to kind of point, thanks Ben, maybe to point this out is that there's, you see this cropping up over and over again in a lot of sort of high level reports, and that, these sort of technologies are really too immature or still in their early stages to be able to inform public policy. And I think that's absolutely right. The problem is that it's always going to stay that way unless we really do something about it in terms of sort of mobilizing both people and finance and skills into this space. So in some ways, this, my talk is a call to action to anyone who's really interested in this area to really get involved, and because we do need the support to push these ideas forward. Okay, and I'll just leave you with maybe one interesting bit of science that I think we're not working on in Heriot-Watt, but I think really sort of push this field forward, and that's really the grinders require grinding. And that obviously takes energy, but what's really interesting is that technology is really efficient. That sort of high energy, high increases the reactivity of the mineral, and there's really the more surface area you go, the really poorer the efficiency is. So a lot of high energy grinding technologies are really less than 1% efficient. And even just pushing that efficiency up from less than 1% up to something like a couple of percent could be revolutionary in terms of mineralization. And that's the same sort of efficiency improvement that the university I'm at, Heriot-Watt, James Watt, made the same efficiency improvement with the steam engine back in the 1800s. It was a few percent, but that obviously revolutionized industrial processes and the Industrial Revolution. So I'll just leave it there. Maybe it's food for thought. Thanks a lot.
Thanks a lot. Thanks a lot, Phil. It was super interesting and fascinating. So there's one. I'll start with the first question in the chat, which is, I think, is a very simple one, but is to really try to. Could you explain a little more in detail how the mineralization process works and how it enables the CO2 capture? And I think what I understand in that question is maybe sometimes there might be a confusion between using mineralization as a storage vector versus using the mineralization process as the capture and storage tool. It's linked, but it's not exactly the same. So maybe can you dive a little more about how it actually happens?
Yeah, okay. So a lot of the minerals that we're interested in, so things like basalt or olivine, when we're thinking of natural materials, they're chemically unstable at the Earth's surface. They were produced deep in the Earth, and when they sort of come out of the Earth, they're unstable. So what they thermodynamically want to react with CO2. So what happens is CO2 dissolves in rainwater. So this is the natural process. CO2 dissolves in rainwater and slightly acidifies the rainwater. It's the acid within that rainwater that then dissolves the mineral. So what you essentially end up with is hard water. So it's water that has calcium and magnesium in it, and it also has bicarbonate. Now, if you get enough of that bicarbonate in water, eventually you'll precipitate out, you'll form a new carbonate mineral with the CO2 locked inside of it. I mean, the distinction between whether it's a capture process or whether it's a storage process, I don't think is really that important. I mean, these reactions can happen at atmospheric CO2 concentration. So you don't need to necessarily concentrate your CO2. It just takes a longer for those reactions to take place. So in some ways, that's what I was kind of getting at with the axis between passive and intensive. You can facilitate these reactions at low partial pressure CO2, in which case you don't need that sort of capture step like a direct air capture system. But on the other end of that axis, you have got potentially direct air capture systems like Climeworks and Carbfix, where they purify the air CO2 and then they inject that for reaction. And that's important if you need the reactions to happen quicker. Hopefully that answers the question.
No, that was perfect. And last question, I think we're running like 5 minutes late, but I think that's fine. So question from Silva, who asks basically, so with mineralization, the kinetics makes the process very slow, especially at surface conditions. And when you scale it, it might be tricky to track every single ton of CO2 stored, because especially when you spread a lot of material on very large surfaces. So how do you think this means? What do you think this means for the commercialization of mineralization? And is it possible to sell a CO2 credit before it's actually stored based on projections? How do you build trust on these techniques? So it's basically an NRV question, I guess.
Yeah, it's a good question as well, and I suppose I think characterizing the reactions as slow is maybe not the right way to think about it. I mean, they are compared to maybe a lot of conventional chemical engineering processes, but in some ways the rate of reaction doesn't really matter as long as you can facilitate it on a timescale that's relevant for policy, right? So and that's sort of years, from years to decades. So it really depends on how you facilitate the reactions. You can speed them up to the point where they do work on relatively short time periods. So specifically for artificial materials, for natural materials, it might take a longer to happen, but it might be sort of on an annual to a sort of decadal timescale. In which case you might want to change the way that the incentive structure works for those projects. So it might be more from a sort of an agricultural perspective, and how you incentivize carbon accumulation within those environments.